Alright, so let's do an example of this. So we're going to calculate, example, what we're going to have is, they want us to find the surface area, I'll just abbreviate, of the cone, x squared plus y squared equals z squared, lying above what? We have x squared plus y squared is less than or equal to 4. So what we're supposed to do is calculate the following. And we have, okay. Alright, so this is what we're supposed to, even though I didn't write it here, we're supposed to find the surface area, first of all, of the cone. Okay, surface area of the cone is the first objective, so that's part A. And part B is calculating this. Okay, where this is our, sorry, I put an A. It's supposed to be a B. This is part B. Okay, where this is our f of x, y, and z. Alright, so starting with part A, we're going to find the surface area. So surface area, again, surface area is going to be given by integrating over the domain, double integral over the domain, and taking the magnitude of the normal, and then integrating that with respect to u and v. Okay, so what we need to do, and in most of these problems, is just the first thing you do is calculate the tangent vectors, and then find the normal. Okay, so let's do so. But first of all, we have to have a parameterization, right? So parameterization of a cone. Alright, so it's kind of going to be similar to a cylinder, since they all involve circles in some way. But in this case, what we're going to have instead of z, instead of an r, like a constant r, what we're going to have instead is the following. So we have some g of theta and t. Okay, so not a z anymore, but a t. And this is going to be t cosine theta, t sine theta, and t itself. Okay, so this is the standard parameterization of a cone whenever you have any cone. And also, so then we have the bounds go from, theta obviously goes from 0 to 2 pi, because it has to go all the way around the circle, right? We want the whole circle all the way around. And then we have to find the bounds for t. And so now we're going to utilize this information here, and we're going to plug in the x and y. So this is our x, that's our y, and this is our z. So if we plug in x and y into these, we get t times cosine theta squared plus t times sine theta squared is less than or equal to 4. So when you simplify this, we get t squared times essentially cosine squared theta plus sine squared theta, which is a 1. And then so we get t squared is less than or equal to 4. So t has to be less than or equal to 2. Okay? And naturally, since this is like a radius, basically t is acting like a radius, so it is going to have to be greater than or equal to 0 as well. So these are our two bounds on the variables, on the parameter variables. And now we have to find the tangent vectors of... Okay, so at this point we're going to, I'll start with the tangent vector with respect to theta. So that's going to be just the partial derivatives of each of these components here with respect to theta. So the first one's going to be a negative t sine theta. The second one's going to be a positive t cosine theta. And the last one's just going to be 0, right? So then the other one, with respect to t, that one's going to be a cosine theta, a sine theta, and a 1. That's a comma. Okay? Alright, so now with these, we have to find the normal vector, and we do so by taking the cross product. So I'll do that on the next slide. So we're going to set up the cross product, and we get n equals t of theta crossed with t sub t. Okay, and then this is going to be, we're going to set it up, the ijk thing, Oop, that's supposed to be a j, sorry, j and k, okay? And then we're going to set up our vectors. So the theta one goes first, so that would be a negative t sine theta here, a positive t cosine theta here, and a 0. And then we have a cosine theta, a sine theta, and a 1. Alright? So something like that. Okay? And then now we're going to take the determinant. So that's going to look like I times, I'll probably run out of room here, but I times, then we're going to focus only on this box here. So then the product of these two are t cosine theta. And then we have minus 0, so that'll just be like that. And then we have a minus j hat. And this one's going to be just focusing on the outer ones. So we're going to multiply the far ones here. So that's a minus t sine theta. And then minus 0. So again, that's just it. And then the last one is our k, so I'll write that one down here. Plus k hat times, now we're focusing on this little box down here. The first product is a negative t sine squared theta. And minus a t cosine squared theta. Okay? So what we get as our normal vector, that's going to be equal to a t cosine theta, a t sine theta. This is positive because the two negatives here cancel. And lastly, we have what this is if you take out a negative t, then we get times sine squared theta plus cosine squared theta. So, and this is just 1, so we get a negative t as our last component. Okay, so we found the normal vector, and now what we really need for the surface area is the magnitude of the normal vector. So let's find that next. So we have magnitude of the normal vector, and that's just going to be the square of all of these added together separately, and then square root the entire thing. So we're going to have t cosine theta squared plus t sine theta, quantity squared, plus negative t quantity squared. There's a negative here. And then square root the entire thing. Okay? And what you get here is t squared. Okay, so I'll just write out t squared cosine squared theta plus t squared sine squared theta plus a t squared, all under the square root. And then here you can factor out 1t squared. So that'll be a t squared times cosine squared theta plus sine squared theta, and plus another t squared. So this is just 1. And what we ultimately get is square root of 2t squared, because you add them. And so this is a square root of 2 times t. Okay? So this is the magnitude of the normal vector. So we have this component now. And all we need, and we found the bounds on the last one, so now we're just going to set up our integral. So again, our t ranged from 0 to 2, and theta went from 0 to 2 pi. 0 to 2 pi. Okay? So now we can set it up, and I'll set it up here, and we'll continue on the next slide. So I'll do the t's first, so 0 to 2, and then I'll do the thetas, so 0 to 2 pi. And now in here we have the magnitude of the normal vector, which is square root of 2t. And then we have d theta dt. Okay? So now we'll just solve like a normal double integral. So we'll do the inside one first. So we are integrating with respect to theta. So all of this in here is basically a constant. So we can bring it outside. So that'll just be 0 to 2, and then we'll bring this outside of the parentheses. So this will just be theta, as theta ranges from 0 up to 2 pi. Okay? And then dt. Alright? Okay, so then I'll continue this on the next slide as well. So what we get is, I'll just bring the radical 2 out in front all the way because that'll always be a constant. Then we have 0 to 2, and then t. And then we get 2 pi minus 0, which was just 2 pi, and the dt. So then outside we have, I'm going to bring this 2 outside with the radical 2. 2 radical 2, and then 0 to 2, t. Oh, I could also bring out the pi. So that'll come out as well. Alright, and then a dt. And then we'll integrate this last step here, and we get 2 times radical 2 pi. And then this is a 1/2 t squared, as t goes from 0 up to 2, all right? And this 2 here, that 1/2 and this 2 cancel, and we get a radical 2 pi, and then a 2 squared minus 0 squared, which equals 4 times square root times pi. Okay, so that is the answer for our surface area. Our surface area, abbreviated by SA, so surface area. So this is part A, and sorry it was so long, but I feel like it's very helpful to see examples of different things, even if they are long, because that's pretty much true to these problems. They're pretty long. But okay, so now we'll start on the second part, part B. So part B asks us to find the surface integral, but this time our f of xyz is this thing, and then ds, of course. So this is f of xyz, that is equal to x squared times z, all right? And again, we have our same parameterization we're working with here. So that'll just be our t cosine theta, t sine theta, and t, because we're, this is, again, just as a reminder, this is parameterization for a cone, okay? Okay, so now let's find f of g of theta t, okay? So in this case, what we're going to do is plug in everything, so x, we're going to write x, y, and z in terms of thetas and t's. So how we're going to do that is, for every x that we see, we're going to plug in t cosine theta. So in the x spot, we're going to plug in t cosine theta, and that'll be in the x spot, right? And then for the z's, we're going to plug in whatever the parameterization tells us to do. So that would be t in that spot, okay? So in this case, our f of g of theta and t are going to be t squared cosine squared theta times t, which is t to the third cosine squared theta. All right? So now, this is our f of g of theta and t, and we already know our normal, the magnitude of our normal is square root of 2 times t, and we already have our bounds, right? T goes from 0 to 2, and theta goes from 0 to 2 pi. All right, so now we can just write out our surface integral and compute. So we have 0 to 2, and then 0 to 2 pi, and then I'll plug in our t to the third cosine squared theta, and then that's times our magnitude of the normal, so that's radical 2t, all right? Then we have a d theta and a dt. Okay, so now I'm going to bring out the radical 2 in front, just because it's a constant. So radical 2, and then I'll rewrite everything, and I'll combine the t's. 0 to 2 pi, and then we have t to the fourth, right? And then cosine squared theta, d theta, dt. So at this point, you can see that we have an iterated integral. So that means you can solve it in steps. Iterated, remember? So here I'm going to split it up into two separate ones, but them being multiplied together. So I'm going to write all the t stuff together. So that'd be 0 to 2. Those are the bounds for t. And then we have our t to the fourth and our dt. So this is the t, like, parentheses, set of parentheses. And this one will be the theta ones. So 0 to 2 pi, cosine, squared theta, and a d theta. Alright, so here I just grouped them together. And also, just as a side note, here we'll need to know, like, a trig identity. So what cosine squared theta equals, well, okay, I'll write it like this. 2 cosine squared theta minus 1 equals cosine 2 theta. So this is a double angle formula. So to get cosine squared by itself, we just add the 1 over. So we're going to add the 1 over and divide by 2. So it looks like that, right? So we're just going to plug that in for here. So what we have over here is radical 2 just stays in front. And here I'm going to integrate the t part. So that's t to the fifth as t goes from 0 up to 2. And then here, I'm just going to rewrite that as this thing. So 1/2 times all of that. So I'll just write the 1/2 in front for convenience. And then we have 0 to 2 pi. And then a cosine 2 theta plus 1 and a d theta. Okay, so keep this in mind, and I'll continue on the next slide. Okay, so then we have our radical 2 in front still, and then we also have a 5. Okay, so we have a 1/5 and a 1/2. I'm just taking this out from the coefficients of the other integrals as well. I'm just putting them all in front. And then our t to the 5th, when we plug in a 2, we get 2 to the 5th minus 0 to the 5th. Okay? And then we also have the rest, which was, I'm going to break these up into 2 separate integrals so we can deal with them in a simple way, I guess. So then plus 0 to 2 pi d theta, because there's a 1 in front here, right? Okay, so what we have in front going on here is this is equal to radical 2 over 5, and then we have a 1 over 2, but then this 2 to the 5th is 32, and so we can cancel here and get a 16. And then in the integral here, we can do a u substitution. I'll just do that real quick over here because we've done plenty of those. So u equals 2 theta, and then du then equals 2 d theta. So d theta is equal to du over 2. So then what we get here is a 1/2. Well, I guess I'll just, yeah, so that's how you would do it. And then what we get is a cosine of u, and then d theta is then du over 2, right? And then over here, I'm just going to continue integrating. So that's a theta, as theta goes from 0 up to 2 pi, right? And then next step, we're going to simplify further. We get 16 square root of 2 over 5. And here we're going to get a 1/2, factor of 1/2 in front. And then when we integrate cosine u, we get sine u. Okay? And then here that's just going to be 2 pi minus 0. Alright, so what we get is then 16 square root 2 over 5 times 1/2 sine, I'm going to replace this with the 2 theta. So now theta will go from 0 up to 2 pi, and this is plus a 2 pi here. Okay, we're almost there. So then we have 16 square root 2 over 5, and this is going to be 1/2 and then times sine of 4 pi, okay, minus a 1/2 times sine of 0, and then we have plus the 2 pi here, okay, and these are actually going to just go to 0, and so we just have a 2 pi sitting out here, so our final answer is going to be 32 pi times square root of 2 over 5, okay, so that is the final answer for our surface integral when our f of x, y, z was x squared times z. Okay? Alright, so now on to the last topic. So here I want to look at when your parameterized surface is just a graph of the following. So when it's just g of some x, y equals x, y, and then some, I'll call it h of x, y. H of x comma y. So in this case, our z, so this is x is just x, y is just y, and z now is h of x comma y. So z depends on, in some way, our x and y coordinates. All right. So in this case, what we would get, I'll just do like a little introduction to problems like these. Our tangent vector sub x, that's just going to be 1, comma, 0, comma, and this is going to be h sub x, where h sub x is just our partial of h with respect to x. Okay, so and we obtain this by taking the partial derivative of each of the components with respect to x. Okay, so similarly for the tangent vector of y, that's going to be 0 and then a 1, and then h sub y, which refers to partial of h with respect to y. Okay. Alright, so in this case, our normal then would be t sub x cross t sub y. And then setting this up, we get I, j, and a k. And then we get 0, or 1, 0, h sub x, 0, 1, h sub y. And we're going to cross them here. What we get is I times 0 minus h sub x, and then minus a j times h sub y minus 0, so just like that. And then our last one is k, and that's just going to be times 1 minus 0. Alright, so our normal vector is going to look like negative h sub x, negative h sub y, and a 1. Alright, so again, these are just the partials of h with respect to x here, and with respect to y here. Alright, so then our normal, the magnitude of our normal vector, magnitude of the normal, would just be the following. We would get h sub x squared plus h sub y squared. I'm just not writing the negatives because they'd go away in the squared. So like that, right? And then the final thing here, I just want to write to set up the surface integral. So surface integral, that would be equal to the following. Double integral over d, over domain d of, in this case our parameter variables are x and y themselves, so you'd have to be given bounds on x and y. And then we have some scalar function f, and we would plug in x and y like normal, and then h of x and y for our z component. And then we'd multiply it times the magnitude or the norm of the normal vector. I'll just say the magnitude of the normal vector, which we just found to be h sub x squared. So again, the partial of h with respect to x squared, plus the partial of h with respect to y, plus 1. And then our dx dy, or dy dx. It just depends on your problem. But this is just the standard form when you have a parameterization such as this, where x and y are the same, they stay the same, they're just themselves, and z is a function dependent on x and y. Okay, so that wraps it up for this video on surface integrals. I wish you the best of luck, and I'll talk to you in the next video if you watch.